Hey everyone, so I want to start on 7.1. Just a quick progression. I guess we went from chapter 6, which introduced trig concepts to us and taught us how to solve for or evaluate trig ratios, through to chapter 5, which also taught us how to manipulate more trig expressions and trig values, utilize the unit circle a bit more, and more importantly, chapter 5's focus was on how to graph trig ratios. Chapter 7 sort of brings everything together, especially within 7.1. A heavy focus, and I guess the main reason for covering 5 and 6 in my mind to prepare you for calculus is 7.1. So what 7.1 is going to try to do is try to implement certain algebraic aspects within the trig world. We're going to show you how you can manipulate trig expressions and algebraic expressions using trigonometry. In order to do that, you really do need a solid understanding of chapters 5 and 6. Having said that, I'm going to sort of walk you through the couple of slides that I have, which I know there are only 3 slides on 7.1, but they're packed with info, things that might help if you memorize them or just at least understand and know how to utilize them. A lot of them, again, are sort of the grouping or culmination of a bunch of things that we did in prior sections. Starting off 7.1, the first slide, 115, goes through a bunch of trig identities. This is, I guess, one slide that has it all. In terms of understanding reciprocal identities, we know that sine, cosine, and tangent are related to cosecant, secant, and cotangent respectively, and we know that they are reciprocals of one another. So if the sine of an angle means the opposite over the hypotenuse side, because we input an angle into the trig ratio and get a ratio of sides, the cosecant of an angle will be the reciprocal, 1 divided by opposite over hypotenuse, or hypotenuse over opposite. That is sine and cosecant. Cosine and secant work similarly, tan and cotan work similarly. Now, we also know through our unit circle that tan of x is equal to, and I used this when we were doing the trig graphing, sine of x over the cosine of x, and cotan of x is equal to cosine of x over the sine of x. Aside from just tan being opposite over adjacent, cotan being adjacent over opposite, we also have sines and cosines in relations to tangent and cotangent. This is going to be extremely helpful and pivotal for us within the trig identity sphere and realm, especially with the trig proofs. Now, these I feel are the easiest and probably the most important to remember, the reciprocal identities. The second most important are the Pythagorean identities, and they come directly after. One of them being sine squared x plus cosine squared x equals 1. Now a quick note on notation. I will explain how we got to the Pythagorean identities after putting up a small unit circle in a second. But on notation, when we have sine squared x, we write it this way. We do not write sine of x quantity squared or sine of x squared. If you were to see sine of x squared, that would mean that the angle x is being squared. That's not usually how we as math teachers or textbooks want to test or ask you problems. Typically, we want the sine of x squared, which means sine of x times sine of x. That will be written as sine squared x. Cosine squared x is cosine of x times cosine of x, written cosine squared x. Again, it is not written as sine of x squared like this, because that will confuse people and lead them to think that we're squaring the angle measure, and that's not what we mean here, or not what we want to be done. So that's why we write the square over the n. It looks a little weird. It's not done anywhere else in our class at least, but that's a note on notation. That's what it means. Now, where does this Pythagorean identity or relationship come from? It doesn't make any sense. Sort of seems like I pulled it out of my butt. Well, I didn't. Assume we have our unit circle of radius 1, right? And there we go. I have a radius equal to 1. Now, as we discussed in the unit circle section, the point here, x comma y, right, will have a y value and an x value. And we know, since it's a 90-degree angle, and this is the angle theta, that the sine of theta is equal to the opposite side over the hypotenuse. In this case, since the hypotenuse r is 1, it's y over 1, or y. The cosine of theta is equal to x, or over 1, which is x. Now, this happens to be a right triangle where the hypotenuse is equal to 1. If we think back a little bit, there is a relationship that governs the sides of a right triangle. It is the sum of the sides, or the legs squared, equals the hypotenuse squared. A squared plus b squared equals c squared, Pythagorean theorem, all telling me the same thing as what I just said. This leg squared plus this leg squared should be 1 squared. Or x squared plus y squared should equal 1 squared. Now 1 squared is equal to 1. X squared, well, another way of saying x is cosine of theta. So I have cosine of theta squared plus y squared, which is the sine of theta squared. Well, if I rewrite this as cosine squared theta plus sine squared theta equals 1, that's my trig identity, my Pythagorean trig identity. So this Pythagorean identity comes from the unit circle. It comes from drawing out a right triangle in the unit circle. You're not responsible for the derivation usually. You are responsible for understanding this formula. It's going to show up in calc. If you don't know it, you're going to get, the butt kicked out of you in certain places. Depending on the background and the types of questions that are asked of you, you might have to substitute. And if you don't know this relationship, you're really going to get slammed. Sine squared x plus cosine squared x equals 1. Very important. Now the other two Pythagorean identities stem from this one. So I don't really need this unit circle anymore, right? We understand that the x value squared plus the y value squared is 1 squared, and the x value is related to the cosine of theta, and the y value is related to the sine of theta. So that's really where this Pythagorean identity came from. Now if I take the base Pythagorean identity and start working my algebraic magical wand, if I take sine squared theta plus cosine squared theta equals 1 and divide the world by sine squared theta, which means I divide every term by sine squared theta. Well, what's sine squared theta divided by itself? 1. Cosine squared divided by sine squared. Cosine over sine is tan. Cosine over sine times cosine over sine is, cotan squared theta. And 1 over sine squared theta, well, 1 over sine is cosecant. 1 over sine squared is cosecant squared. Because 1 over sine squared is 1 over sine times 1 over sine. Right? How do we get sine squared? Sine times sine. So it's cosecant times cosecant, or cosecant squared. This happens to be another one of my Pythagorean identities. It is the third one on the list. So if I took the original and divided everything by sine, I get the third Pythagorean identity. And if I take my original and divide everything by cosine, let's assume I divided everything by cosine squared theta. Sine divided by cosine is tan. Sine squared divided by cosine squared is tan squared. Cosine divided by cosine is 1. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared theta. And we'll see that this is the second Pythagorean identity on the list. So I can derive the other two based on the first one. I never memorized the other two when I was in your shoes. I really only knew this one, and then was able to derive the other two based off of this one by either dividing the whole equation by sine squared or the whole equation by cosine squared. It's up to you. You guys prefer memorization, you can definitely do it. Even or odd properties, I'm not going to spend too much time going over. That was in 5.2. We definitely learned the even and odd properties of sine, cosine, tangent, secant, cosecant, cotangent. Cosine happened to be the only even trig function, along with its reciprocal function, secant. So the cosine of a negative angle is the cosine of a positive angle. Important for trig identities, very important for calculus. Now if I had limited RAM space or storage in my brain, what I would focus on would be these first three tranches: reciprocal identities, Pythagorean identities, and even or odd properties. Co-function identities I'm not even going to bother going over, right? Not a focus in my classes. I'm not sure how many people focus on it in calc or in later stages, right? Okay, having said that, so let's move on to the next slide. Let's look at 116. We're going to be looking at simplifying certain trig expressions. So basically we're going to be utilizing this information to put pieces of a puzzle together. Now, we might not necessarily make something look simpler. Part of the game is just really translating or making it look like something else. So if I want to make one expression look different or look like another expression, that might be useful. And that's what all of this stuff on the slide 115 is for. So if I want to simplify cosine of t plus tan t times sine t, how am I going to go about doing it? Well, sometimes it's useful to convert tangent to its reciprocal function form. So I'd have cosine of t plus sine t times sine t. And this is sine t over cosine t, I'm sorry. So I'm converting tan to sine over cosine. Now a fraction times a value is numerator times numerator. So I'd get cosine of t plus sine squared t over cosine of t. So far it doesn't look like I was able to simplify. I have two terms here, I still have two terms. Now how do I add a fraction to a non-fraction? I need an LCD. So it's important that you guys realize, in order to do most of these problems, what you're going to have to do is use basic algebraic skills. One of them is, if I have a fraction times a value, I multiply the numerators when I'm multiplying fractions. If I want to add a fraction to a non-fraction, I need an LCD. The same math applies. LCD is cosine. So I have to multiply this guy by cosine over cosine. I get cosine squared t over cosine of t plus sine squared of t over cosine of t. Now that I have the same LCDs, I can add the numerators. I get cosine squared t plus sine squared t all over cosine of t. Now you think to yourself, okay, I wrote two terms as one expression. It doesn't really look simpler to me, but I was able to combine them. Now we really need to think and look back on slide 115, or just rack our brains for a bit and think, okay, I have cosine squareds and sine squareds together. Do I have a relationship between the two? Yes, I do. Sine squared plus cosine squared equals 1. So this equals 1 over cosine t. And 1 over cosine, based on our reciprocal functions, is equal to secant of t. That means this original expression could have been rewritten or expressed simply as the secant of the angle. And that's the value add here. Through a little bit of traumatic algebra, trigonometry, overall math trauma, we can simplify an expression to make it go from this nonsense to that nonsense. Right? We did it by translating tangent and then trying to combine two terms by getting an LCD that matched and then using a Pythagorean identity. Let's try another one. Simplify sine of theta over the cosine of theta plus the cosine of theta over 1 plus the sine of theta. So here again we have two fractions. How do we add fractions? We need an LCD. LCD seems to be the cosine of theta times 1 plus the sine of theta. So let me multiply this fraction, sine of theta over cosine of theta times 1 plus the sine of theta. And this guy, cosine of theta over 1 plus the sine of theta times cosine of theta. Now I'm not going to multiply out the denominators. I'm going to actually leave that in factored form, but I will distribute the numerators. Sine of theta times 1 is the sine of theta. Sine of theta times sine of theta is sine squared theta. That's going to be over the new LCD, which is cosine theta times 1 plus sine theta. This is cosine times cosine, which is cosine squared theta, over the new LCD. I don't want to write it out. Then we have the same LCD, cosine times 1 plus sine. So let's add the numerators now that we have the same LCD. I get sine theta plus sine squared theta plus cosine of theta, squared theta, divided by cosine theta times 1 plus the sine of theta. Now I notice that a portion of my numerator has a Pythagorean identity attached to it. Right? Sine squared theta plus cosine squared theta now equals 1. So I could write this as sine theta plus 1 over my LCD, which is cosine of theta, times 1 plus the sine of theta. Well, I guess it paid out by not multiplying out the denominators. I just had the same LCD and I kept it through. Because now I see that the LCD has a factor that's common with the whole numerator. Sine theta plus 1 and 1 plus sine theta are really the same thing. So I can factor that out and that equals a 1. 1 times, so I get sine theta plus 1 over sine theta plus 1 times 1 over cosine of theta. And this factors out. That's equal to 1. 1 times 1 over cosine theta. And 1 over cosine of theta is equal to the secant of theta. So yet again, I found another crazy looking expression that's equal to one term. So just a few hints. Almost always, if I have tangents or cotangents or secants or cosecants, I want to put them all in terms of sine and cosine, and we're going to get to that in the next slide. But I also see here when I have fractions, sometimes it pays to make an LCD and combine them. Keep track of your Pythagorean identities. See if you can factor things out at the end. All of this will play a role in your ability to solve trig identities or simplify trig expressions. So what that slide 116, was focused on was giving you expressions. These are expressions. There's no equal sign yet, right? And simplifying trig expressions is very similar to what we're going to do on slide 117, which is proving trig identities. Usually a 10 to 15 point problem on a final. Probably some of the hardest stuff that students struggle with in the course. Why? Because it combines all your knowledge of trig with basic knowledge of algebra, and typically people get lost just because of their general fears of trig, right? But we're going to try to demystify these. When I was a student, I struggled with trig identities until I did about 50 to 60 problems. So you guys aren't going to get these unless you really practice to the bone and beat yourself to a pulp until you do a ton of different problems. When it comes to these proofs, they're sort of mini proofs. How do you do them? I'll walk you through 4 different examples on this one slide. Those 4 examples are really examples that will carry you through a bunch of the different types of trig identities you're going to see. Unfortunately, these are not types of problems where you can use your calculator or check your work using a calculator either. Proving trig identities is basically a way of telling you to prove that the equal sign is true. They're going to give you 2 sides of an equal sign, and they're going to say, prove that these 2 sides of the equal sign really do equal each other. They always do. You just need to prove that one side looks like the other. So it always helps to, and I have a 3-step method here, sort of rewording some of the stuff that you had in your textbook. Pick one side of the equation and try to make it look like the other side. You always want to try to pick the more complicated, the more effed up side, the side that looks like it's on steroids. Take this huge or more intimidating looking side and figure out ways to simplify it to make it look like the other side. Okay? It's almost always easier to peel a shell off of a nut than it is to glue pieces of a puzzle of a shell back onto the nut, right? So I would recommend starting with a more complicated looking side. It's not like, by the way, a formula where I have 7 plus 3 equals 7 plus 3x equals 2x, and oh look, let me subtract the 3x from both sides. Here in these problems, I'm almost always going to ask you to draw a border wall, right? And pretend this is a border wall that nobody can cross. If I draw a wall down, I don't want anything going from the left or the right side. I want this left side to look like the right side. Make it look like the right side without bringing anything over to the right side. And that's a challenge. It's not the easiest thing in the world. So pick one side, make it look like the other. Use algebra and the identities you know to get rid of fractions. Use least common denominators, etc. Don't invent algebra. Use the algebra you know, and I'll walk you through several problems and show you common mistakes that students have. It's usually useful to convert everything into sine and cosine to make it easier, right? Tangent is sine over cosine. Cotangent is cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. So whenever you have trig expressions that are not in sine and cosine, sometimes it's better to convert everything to sine and cosine, because then it's just easier to manipulate. And we'll see more examples of this in 4 examples that I put up. So let's check out the first one. Verify that the cosine of theta times secant theta minus cosine theta equals sine squared theta. So as always, I'm going to put up a wall and say, let's assume that I have space to work on the left side or the right side. I'm going to choose the left side because it looks more complicated. I don't want to touch the right side. I want to make this left side equal sine squared theta somehow by not bringing anything over to the other side. How am I going to do it? Well, let me use one of those three pieces of advice on the beginning portion of the slide. Let me convert secant to 1 over cosine. So I have cosine of theta times 1 over the cosine of theta minus the cosine of theta. Next, I'm going to use another common algebraic thing that we learned earlier in the semester, the distributive property. Okay? And I'm not reinventing math. I have a value outside of parentheses. I can distribute it amongst both parts of the parentheses. Cosine of theta times 1 over cosine of theta minus cosine of theta times cosine of theta. Now cosine times 1 over cosine, the cosines just factor out or cancel and I have a 1. 1 minus cosine times cosine is minus cosine squared theta. So now I have 1 minus cosine squared theta. And you start thinking to yourself, well, what the heck do I do here now? Whenever you see a sine squared or a cosine squared or secant squared, cosecant, cotan, tan squared, look back at your trig identities. Now again, you're not going to be getting open book exams necessarily, but when I have 1 minus cosine squared, I think back to my Pythagorean identity, sine squared theta plus cosine squared theta equals 1. Okay, I have 1 minus cosine squared. So let me subtract the cosine squared from both sides. And this is an aside. If you guys ever took Shakespeare, Shakespeare had these asides where he pulled you to the side and started talking to you as if nobody on the stage knew what the heck you were talking about. So I write this off to the side. It's not part of my standard proof, which goes line by line. I want to show you that sine squared plus cosine squared is equal to 1. If I subtract the cosine squared from both sides, sine squared of theta is 1 minus the cosine squared of theta. So that now where I'm at with 1 minus the cosine squared of theta, if I just write sine squared of theta, it doesn't look like I pulled it out of my ass. I actually proved it to you. I showed you where it came from. Here. So 1 minus cosine squared theta is equal to 1 minus cosine squared theta is equal to sine squared of theta. And I'm trying to prove that this left-hand side equals the sine squared of theta. And I'm able to do that successfully without bringing anything from one side of an equal sign to the other. Okay? So first type of problem you get, standard plug and chug, right? Just convert secants potentially, multiply out, distribute, use your standard algebraic tools, use your reciprocal identities and your Pythagorean identities, swap things out and make the left hand side equal the right hand side or vice versa. Next problem. Verify that 2 tan x secant x equals 1 over 1 minus sine x minus 1 over 1 plus sine x. Now if I had to look at this and say, okay, which of these two sides is more intimidating, I would probably choose the side with the fraction and try to work out the right hand side. 1 over 1 minus sine x minus 1 over 1 plus sine x. I need an LCD. The LCD is going to be 1 minus sine x times 1 plus sine x. So I know that I'm going to have 1 plus sine x times 1 in the numerator and 1 minus sine x, 1 plus sine x here. So I multiplied numerator and denominator here by 1 plus sine x. And here, I'm going to multiply numerator and denominator by 1 minus sine x. And I get 1 plus sine x minus 1 plus sine x, because I distribute the minus. So I would have gotten 1 minus sine x. This would have been a minus 1 plus sine x here. Again, multiply this out and then distribute the minus so that you can bring everything together because it's under the same LCD now. And I get 1 minus sine x, 1 plus sine x. Here I'm going to combine. 1 minus 1 is 0, sine x plus sine x is 2 sine x's. Here I'm actually going to FOIL out because I don't have 2 sine x's being something that can cancel out with 1 minus sine x or 1 plus sine x. You see, it looks like a factored form of a difference of perfect squares, and it is. 1 times 1 is 1. 1 times sine x is sine x. Negative sine x times 1 is minus sine x. So those two middle terms cancel. Minus sine x times a plus sine x is minus sine squared x. Now again, we have our little Shakespearean aside, because I have sine squared x here, and I don't know what else I can do here. Now I can't divide 2 by 1 minus sine squared x and sine x by 1 minus sine squared x and multiply. It's not going to give me anything. But 1 minus sine squared x, I know that cosine squared x plus sine squared x equals 1, and cosine squared x is 1 minus sine squared x. So let me convert 1 minus sine squared x to cosine squared x. That gives me a 2 sine x over cosine squared x. Now again, my ability to do this quick and on the fly only stems from my experience and having been able to do these problems for years and having done a ton of them. You guys will only get this good after doing a crap ton of practice problems. Because how else would 2 sine x over cosine squared x look like this? Now check it out. Cosine squared x is really cosine times itself. So I have 2 times sine x over cosine x times cosine x. Now in the world of multiplying fractions, 7x over 12 can be broken up to 7 over 4 times x over 3. Because when we multiply fractions, we multiply straight across. So having said that, I can convert this to a 2 over 1 times sine over cosine times 1 over cosine. Because again, if I were to multiply across, I'd get back to the line above it. And that's the point here. I'm only working down one side of an equal sign. If I wanted to work my ways back, I should tie to every line prior, if I ever had to work backwards. And I see that 2 over 1 is 2, sine over cosine is tangent, and 1 over cosine is secant. So I now equal the left-hand side of the equation, 2 tan x secant x. So let's recap. I started off with 2 fractions. To combine the 2 fractions, I needed an LCD. The LCD is this denominator times that denominator. So I multiplied every term in this fraction with this denominator and every term in this fraction with this denominator to get that. I got here. Then I started combining things. Well, I multiplied by 1, I multiplied by 1, and I subtracted to get one numerator and over the same LCD. So now I have one fraction. Now I want to simplify the fraction. So I add the like terms in the numerator to get 2 sine x. I FOIL out the denominator to get 1 minus sine squared x. I notice that this doesn't equal that. I got to work further. Well, this can be replaced via Pythagorean identity. You get here. Now to go from here to the final answer requires some fancy algebraic footwork. But now that you've seen what you can do, you can replicate it. Cosine squared is cosine times cosine. 2 sine over cosine times cosine is 2 over 1 times sine over cosine times 1 over cosine. You get 2 tan x secant x. Third problem. Cosine of u over 1 plus the sine of u equals secant u plus tan of u. So here, I'm going to choose to work down the left-hand side. Now another shortcut that I would give you, if you guys remember how to rationalize the denominator, you multiply the numerator and denominator by the conjugate pair. We're going to do the same here. It looks weird because I don't have a radicand, but we're going to see here with trig, sometimes it helps us when we have a trig fraction and I have 2 values in the denominator and 1 value in the numerator. So it's not like I could break this up into a product like I did the last problem. I have 1 plus sine u in the denominator. I'm going to multiply by 1 minus sine u. And we're going to see why in a second. 1 minus sine u, 1 minus sine u. Now here, in the numerator, I'd get cosine of u times 1 minus sine u. I don't want to multiply it out just yet. Here I get, again, 1 plus sine u times 1 minus sine u. Let me FOIL that out. I get 1 minus sine squared u. Well, using our Pythagorean identity, we already know that cosine squared u would be 1 minus sine squared u. Because cosine squared plus sine squared equals 1. So if I move the sine squared over to the other side by subtracting from both sides, I can replace this with a cosine squared. So cosine u times 1 minus sine u would be over cosine squared u. How does that help me? Well, cosine squared u is cosine u times cosine u. So let me bring this side up here. I have cosine u times 1 plus minus sine u over cosine u times cosine u. Since this is a product and this is a product, I can factor out one of the cosine over cosines. And I get a simplified expression of 1 minus sine u over cosine u. Now you think to yourself, okay, you did all of this algebraic work. We multiplied this fraction by the conjugate pair of the denominator. We did that here in the numerator, and in the denominator we got the difference of perfect squares. Fine, we were able to use a Pythagorean identity to substitute. Great. Then we factored out the cosine squared to cosine times cosine just to get rid of one of the terms in the numerator. Wonderful. How does that help me? Well, again, think back to our basic algebraic concepts. If I had 7 plus 3x divided by 4, how did I get 2 terms in the numerator divided by 1 term in the denominator? Well, it used to be 7 over 4 plus 3x over 4. I was only able to add them because I had the same LCD. Same concept here. 1 minus sine u over cosine u is 1 over cosine u minus sine u over cosine u. I was only able to write them as 2 terms in the numerator because I had the same LCD, and when I have the same LCD for 2 fractions, I could combine, add or subtract. Now it makes sense. Divide every term in the numerator by the denominator. 1 divided by cosine is secant. Sine divided by cosine is tangent. Secant u minus tan u. Don't know why I have an x there. Okay, forgive me, I copied this wrong. This should have been a minus from the beginning. That would have made this a plus, and that a plus, and that a minus. I copied it wrong from the slide. Would have made that a plus. That's still a minus, because it's a difference of perfect squares. That would have been a plus. That would have been a plus, that would have been a plus, that would have been a plus, and that would have been a plus. And I have secant u plus tan u here. Last example. One plus cosine theta over cosine theta equals tan squared theta over secant theta minus 1. So here where I usually tell people, hey, have a hard dividing line and work out one side, we see in this problem both of these seem to be semi-complex, right? They're both fractions, they both look a little bit the same. This is one term, that's one term. So I'm actually going to deviate from plan a little bit, and I'm going to work or whittle down both sides of the equation a little bit to see if I can get to some happy medium. 1 plus cosine over cosine, I'm going to start there. Just like we did in the last problem, this came from 1 over cosine plus cosine over cosine. Because in order to have two terms in the numerator, I had to have two separate fractions. Well, 1 over cosine is secant. Cosine over cosine is 1. Can't really do anything with this. This is not a squared. I don't have any Pythagorean identities that are secant theta plus 1. I have to leave that where it is. That seems pretty simple to me. It seems like it's been simplified to the core. What about the next one? So let's take a look at the right side. Tan squared. Well, again, this is squared, so maybe I have something on my Pythagorean identities sheet. You go back and you look, and you think to yourself, okay, even if you don't remember the identities, sine squared theta plus cosine squared theta equals 1. In order to get a tan squared, we need sine over cosine. So let me divide everything by cosine squared theta. Sine over cosine is tan squared theta. Cosine over cosine is 1. 1 over cosine is secant squared theta. So tan squared theta would be equal to secant squared theta minus 1. That would be another Pythagorean identity that you could have done off to the side. You could have started here if you memorized them. But you can say, okay, let me substitute for tan squared theta. Secant squared theta minus 1 over secant theta minus 1. Now how does that really help you? You just substituted one term for two. And why would you do it? Well, just like we had in the prior problems when we had a difference of perfect squares, we'd write, instead of 1 minus sine squared, we'd write cosine squared. Sometimes it's actually better for us to have a difference of perfect squares because we can then factor it. Secant squared theta minus 1 can be factored to secant theta plus 1 times secant theta minus 1, right? A squared minus b squared is a plus b times a minus b. So if I have secant of theta plus 1 times secant of theta minus 1 over secant of theta minus 1, well, don't these two terms cancel? Common factors in numerator and denominator. So I get secant of theta plus 1. Well, hey, look. Secant of theta plus 1 equals secant of theta plus 1. So if I start with two fractions and whittle down the left side and whittle down the right side so that the left side equals the right side and I never transferred anything over, that's also okay. And in some cases you're gonna have to do that. And that's when the left hand and right hand side are sort of equal in complexity. Okay. I'm going to briefly go over 7.2 now as well, because it's a one-slider, and then we're done with course materials. And you guys can email away with questions on any of the stuff that we've covered to date. 7.2, addition and subtraction formulas. The reason why I want to add it on to this section is because these aren't really ever formulas that I force you to memorize. If I were to ask them to you in the form of a multiple choice question, for instance, I would provide you with the formula. But they're somewhat useful. And I don't know if in calc you're going to be forced to memorize these, but let's just take a look at the first four. What are they trying to tell me? And I'm going to put one of these on the board and show you how to do a specific problem. Let's, for instance, look at the cosine subtraction formula. Cosine of s minus t equals cosine of s times the cosine of t plus the sine of s times the sine of t. Again, the other three formulas for sine and cosine, addition and subtraction are somewhat similar in what they tell us. The formulas are different, and again, you're not going to be forced to memorize these in my class, but what are they telling me? And why are they useful? Well, they're telling me that if I were to take one angle and subtract it from another angle, I could instead replicate or write out that combination this way. How the heck does that help me? Right? Some of you are looking at this and saying, okay, this doesn't really look like it's something that I would ever want to mess with. I want to actually do the addition formula, cosine of s plus t. It's cosine s cosine t minus sine s sine t. Similar type of thing. How would this ever help you? Well, if you're ever asked to answer questions algebraically only, this will sort of expand your scope. Let's look at example 1. If I ask you to find the cosine of 75 degrees, algebraically, without using a graphing calculator, how would you do it? He only gave us 45, 45, 90 triangles and 30, 60, 90 triangles. How could we find the cosine of a 75 degree angle? If I draw out a 75 degree angle, the reference angle is the 75 degree angle. I can't do it algebraically. It's a trick question. No, it's not. If you think 75 is equal to 45 plus 30, then you could actually break this up. The cosine of a 45 plus 30 degree angle would be the cosine of the first angle s, or the cosine of 45, times the cosine of 30 minus the sine of 45 times the sine of 30. Now here you could already draw out your 45, 45, 90 triangle with the ratios of sides x, x, x root 2, and your 30, 60, 90 triangle with the ratio of sides x, x root 3, and 2x. And say, okay, the cosine of 45 is adjacent over hypotenuse, x over x root 2, 1 over root 2. I'm going to multiply that by the cosine of 30, adjacent over hypotenuse, which is root 3 over 2. Then we're going to subtract the sine of 45, which is opposite over hypotenuse again, 1 over rad 2. times the sine of 30, which is opposite over hypotenuse here, 1 over 2. What do I get? Root 3 over 2 root 2 minus 1 over 2 root 2, or rad 3 minus 1 over 2 root 2. Can all be done algebraically. So again, similarly, we have sine of s plus t is sine s cosine t plus cosine s sine t. Sine of s minus t is sine s cosine t minus cosine s sine t. There's no real smooth way for me to show you how to derive those, and there's no real reason. I don't see this as being a huge component in my class, and I don't think that it translates to calc in a way that they're going to make you memorize this. But again, these formulas are somewhat useful in that you can then break down more complicated angles and increase your ability to do these problems algebraically without the use of a calculator using your special triangles. So we're not just limited to 45-degree angles, 30 or 60-degree angles, or reference angles that are affiliated with them, like a 120-degree angle has a reference angle of 60 degrees. We can now do an angle like 75 degrees, because we could break up 75 to 45 plus 30. Okay? You can do an angle like 120 by saying, hey look, it's 90 plus 30. Right? It's just a different way to look at it. Or a 105-degree angle. A 105-degree angle could be 90 plus, actually I'm sorry, that won't help. A 135-degree angle would be the same. But you can do larger angles that you maybe didn't have the ability to do before. So, yeah, having said that, the tangent addition and subtraction formulas are here as well. And you can walk yourselves through those problems. If you have any issues, please feel free to reach out. 7.1 and 7.2 is where we finish off chapter 7. After this, if any videos go up, they're going to be on homework problems that you guys request. So please feel free to reach out with any questions.